previously we took a look at to see if there was significant regression or significance that two random variables did have a potential relationship by looking at that hypothesis test related to the slope being equal to 0. And if we could rule out that under that, reject that null hypothesis, that was 0, hey, then we had potentially a regression relationship that we could form. Now, there's another way to do that, and that's with this analysis of variance approach, which is in some ways going to be a snapshot ahead or into time of what we're going to do in the last 2 modules of the semester as an introduction, because you can do an entire course just on the analysis of variance alone. The key thing for us is that we're going to look at our response variable and its variance and break apart the variance into 2 pieces, and a variation explained by the regression line and the unexplained or leftover variation formed by the residuals. We're going to go back a little bit to sort of a fundamental view of the data, and before we start getting into equations and breaking apart the alphabet soup of our data processing. So let's go back to just a simple understanding of that we have a regression line, and remember that that was our conditional mean based upon x. Right? That was essentially what that line was. And if we go back and just think fundamentally about the variation that we have, just say in x alone, not even thinking about it being jointly paired, but just based on the marginal of x, maybe we get a normal distribution, which I've reflected mirrored down here at the bottom. There's your mean of x, right? And then your some sort of standard deviation of x as well. And we could think about that in the same kind of sense over here for our response variable as well. Okay, and if we have the case that our population correlation coefficient is 1, that says that we have a perfect linear relationship between the 2 random variables, that y is equal to mx plus b. Right? And therefore the conditional mean of y then is going to be equal to this slope parameter m times the mean of x plus b. I should really say wherever the x value is that we're at. But if we're just looking at here with correlation coefficient of 1, and we want then the mean of y, then forget about the conditional stuff. It'll be just directly this right there, right? That's pure linear relationship between 2 random variables. And if we go look at the conditional variance of y given x, well, that's going to be equal to 0, right? Because we have a perfect relationship, and if we know exactly what x is, then we know exactly what y is going to be, and there is no variation. And so the leftover variation in y is going to be explained entirely by the variation of x. So just functions of random variables is all that we've got in that view of the world. But if rho is not equal to 1, then we're going to have some leftover variation. And remember, we were capturing that in our regression model with the error term that was sitting out here. Error only in the sense that our model didn't predict exactly what the actual y value was going to be. And I've switched back over to the symbols that we've been using before, just to differentiate between what's happening here and what's going on down below. Right? In that case, our conditional variance of y given x is going to be then the error variation. And that, remember, we talked about this at the very beginning, that for a specific value of x, then we get that little spread, and there's your signal y given x. Okay. Now, this little distribution and that one are not the same thing. This is the marginal of y, this is the marginal of x, and this is a conditional of y given x. Right. Okay. All right. So now that's a little bit of this idea that we're going to break apart the variation into two pieces. Right. Now this leads us to a specific identity, which is that, and it's called the analysis of variance identity, that our total variation, and so that's the actual y values minus the sample mean, so that's in a sense dealing with just this marginal over here, can be thought of as being broken apart into two pieces. That associated with the difference between the predicted value and the sample mean, and that portion which is from the predicted value and the actual value. So actual value minus the predicted value squared. And so what we're getting here is that this first part is associated with the regression, and this part is associated with the residual, right? And this part is the total. And that takes us back to some definitions that we had before, that this term on the left-hand side was the sum of squares of the total, right? And this is the sum of squares of the regression. Your textbook just is sub r there. I write it out a little bit more to, because I sometimes use this one as not SS sub e for error, but sometimes I use r here. So because of two different r's, I like to write that out just a little bit more. Okay, and we know that, for instance, this guy here is equal to beta 1 times capital S sub xy, right? And so this is the portion variation explained by the regression line, and this is the portion that's left over, the unexplained portion. One more key thing before we move on with this, and that is that we have a variety of different degrees of freedom here. That this one, remember, had n minus 2 degrees of freedom. This one has n minus 1 degrees of freedom, and the regression sum of squares has 1 degree of freedom. And you can sort of a hand-waving kind of argument here that you can use to understand why is just take a look at what we've got in here, that in the tabulation of this thing we've got predicted values minus sample values, being the y bar, right? So not individual, but both of these reflect having used the data to do lots of calculations, manipulations, right? Versus this is an actual minus an estimated predicted one, and this just is inherent within the data set all by itself, the marginal all by itself. So because of that, this one really only has 1 degree of freedom remaining in it. Okay, that's just a crude hand-waving argument for where that develops and comes about. And so in this notion that we're going to test for significance of regression, we need to go find some expected values and understand what the sampling distribution here might end up being. The expected value of SSE over n minus 2, well, remember that was nothing other than our estimator for the variance of that error, right? And there's that n minus 2 to make this an unbiased estimator. That's where we're getting the n minus 2 degrees of freedom from, right? And Then we find out also that the expected value of the sum of squares for the regression is equal to this error variance plus beta 1 squared s sub x x x. Okay, and critical aspects here are going to be that our error sum of squares divided by our sigma e squared term and our regression sum of squares divided by the same variance term are something similar to what we've seen before, and they turn out to be independent chi-squared random variables. And remember though that when we started talking about this and we took ratios of variance, right, this was hypothesis test associated with variances, that we had to keep track of the degrees of freedom. We got 1 degree of freedom for the regression term and n minus 2 for the SSE over variance term. That's key to keep those. So chi-squared, and we're going to go look at ultimately ratios of things. Now, to get there, to sort of define what the actual null hypothesis is kind of a little goofy and weird. We got to go back to where we were really looking at this, and that was test for significance of regression, and if beta 1, the slope, was equal to 0, then we would conclude that, gee, we don't have any linear relationship. So our null hypothesis is really associated with beta 1 equaling 0, our alternative hypothesis being that it's not. Right? That's why we are looking at this as a test for significance of regression. Right, so it's not so much about a test associated with the interest in the parameter itself, what value might it or might not be. It's really about the special case of it being equal to 0 and what that might be suggesting to us. Right, so now that leads us to that if we have 2 chi-squared random variables, when we go take a look at a ratio of them, we end up with that F distribution, and the test statistic then is the F, and we're going to take the regression sum of squares divided by its degree of freedom. So in a sense there's an average going on there, and then the error sum of squares divided by its degree of freedom. Right, and when we do that, we take the sum of squares and we divide them by their degrees of freedom. We end up with what we call the mean square. And so that's the mean square of the regression and the mean square of the error. Key thing again, and this is why you see this 1 repeated, and it just doesn't seem like you need to, right? I mean, gee, SS reg divided by 1 would just be SS reg, but to emphasize that it's there, it's all about that degree of freedom. And so the numerator has a degree of freedom of 1, the denominator has a degree of freedom of n minus 2. And remember, for the F distribution, that's crucial to have when we go look that up in the tables. And we can't flip-flop those around because we get a different result. It's not a symmetric distribution in that sense. Right? Our rejection rule, or operating rule here, is that if our calculated statistic is greater than our value, in this case it's the F value associated with this alpha, and 1 degree of freedom in the numerator, n minus 2 in the denominator, and so we'll reject if that's the case. We get out there in the tail, our calculated values are that ms reg is equal to beta hat 1 SXY divided by 1, that would, and for our aquifer data, that's 1.3049 divided by 71.6. And oops, I used the intercept value rather than the beta 1 value, so that's 0.9047. And when you calculate that out, that's 64.78. Then our MSE is equal to oh, hey, you know, SSE over n minus 2, that's the same thing as our standard deviation of the error squared. Right, so we actually already have that number. It's 12.483 divided by n minus 2, or 15, and that number we actually already have is 0.8322. Right, and if you take the square root of that, that's the 0.912 that we were using before for the square root of that. Right, and so that means our F statistic that we get is 64.78 divided by 0.8322, and that's equal to 77.84. Then we go look up if we're going to do a 5% two-sided, then that would be, remember, F alpha 1 comma n minus 2. So if it's two-sided, 95%, so 0.025, right, and then that would be 1, and that would be 15. That number, when we go look it up, is 6.20. And so clearly F naught, our statistic, is outside of that, so I know we were doing a two-sided deal here, but we've already found that it's outside. We don't have to go look at the lower bound, and therefore we reject our null hypothesis. Right? And that just says that we do think there is some regression model there, that there is a relationship somehow between the two variables, at least from a statistical standpoint. Right, now, if you really want to go find the p-value that's associated with this, then it turns out that that is approximately 5e to the minus 7. So very, very, very small number here. And remember, the way you have to go do that is then you have to go and work with that relationship that says f sub 1 minus alpha comma uv is equal to 1 over f alpha v u. You have to do that flip-flop back and forth in order to get there, and then you have to play a little bit of 1 minus game as well, and then add what you get from the two tails to get to that particular p-value. Right, now, this is really mostly just a way to introduce a couple of terms here. It wasn't really a particularly significant test. In this particular example, we already had lots of convincing evidence that there was a regression relationship to be developed between the two variables. But when we get into analysis of variance, we'll start to encounter some of these terms, the mean squared and mean square error and the mean square for the regression. And now we've seen that once, so it won't be quite so unique the next time around. And we'll also be looking at a similar kind of identity, this idea that we're going to be breaking apart variation, and keeping track of that's going to be important and crucial as we head on down the path into another whole concept of called this analysis of variance. And that's all about designing experiments, for instance.